My camera? In the fall. All right. So, here's where we were yesterday. Okay, here's where we were yesterday. I would like you to draw along with me. So we had a question that I'm not really sure that we got an answer to. So we were starting with the wall, right? And what do we know about the wall? So what do you notice about the distribution of the pluses and minuses? They're equal. Good, we have equal distribution of pluses and minuses. I'm happy with that. So what's the overall charge? Is the overall charge positive or overall negative? Neutral. Overall neither, so we call that neutral. Is that cool? Yeah. And I'm happy with that. Did anybody rub the wall? No. So, but if I bring my balloon over here and let's go with the Josh assumption. The Josh assumption said, I think what happens is when you rub the balloon with the fur, somehow some excess electrons are transferred onto the balloon. Is that a possibility? We have no idea. Okay, we have no idea. So what we do is we create what's called a mental model in our head of how this thing works. Okay? And then we go with it until we have to modify it or throw it out. But let's start with this and see what happens. So if it's possible with one of the things that we talked about yesterday. One of the things we talked about yesterday was that, I hate when I leave a marker open. So frustrating.
Okay.
So one of the things we talked about yesterday is if this is our model of an atom, then the protons, the positives, are locked inside the middle. They don't get to go anywhere, but the electrons are free to move, and they may move more depending on the object. Is that something from yesterday you're okay with? So would it be possible that if you rub the balloon, some electrons from the fur went out of the balloon? Is that still consistent with our understanding? Mm-hmm. All right, let's do it then. What happens? What happens if you bring this balloon that has an overall excess negative charge? What happens as you bring it close? Check your neighbor now. What's going to happen if you bring it close? Check your neighbor now. Quick, check your neighbor. Check your neighbor. Booyah! Okay, did you check your neighbor?
Yes, I did.
What did she say?
No, I understand that. And that's how I know. How do they do it?
Positive protons, I mean.
Oh, with their
But if they're orbiting, right, then the electrons get passed
They're not orbiting.
All right.
They're not orbiting. There's no orbits. There's no orbits. Get it out.
I know.
There's no orbits.
So get rid of our chemistry knowledge. Got it. Love
They
it.
never told you there was orbits. No.
No, they just drew lines and then like you think there's no orbit.
Then how is this like there?
It isn't there. It's complicated.
It just chill.
It could be
But they
there.
move.
No, it's the
They
link.
move?
No,
Yes.
not necessarily. The link theory.
It could really be anywhere,
They're
but like,
anywhere.
Mr. Hetzler, stop explaining things to people.
Sorry.
No one is listening to
I
you.
know. No, I don't know that.
It's not personal.
no, it's just people
It's not
just draw
personal.
lines, so it's easier like to put them out. So if it's like 8, it's easier to put in a circle.
So
they just make it so it's easier.
here's where you guys are on this, and this is a great place to be, is that what we do in the chemistry classes is we have this idea that we know that we think that there are electrons and protons, but there's no really good way to represent them. Like, I don't know how to represent them. So when you draw like a chemical bond, for example, right? When you draw a chemical bond, what do? Right, you just draw a line between two, but what does the line represent? Really two shared electrons? Does that make any sense at all? I don't know. It's a representation. It is a model we use to try to represent something that is really hard to represent. All right, as you get deeper into chemistry, they say, oh, well, these electrons exist in what we call orbitals. right? And then they imply that there are shapes to these orbitals, like the first two, right? Like the s orbitals
Yeah, it's like a circle.
is like a circle, right? But then the p orbitals are like dumbbells that exist in 3 dimensions.
Yeah.
Yep.
Does that make any sense to anybody?
No.
No, of course not. Of course it makes no
Somewhat.
sense. I don't mind that though, because we're trying to represent something that's really hard. The problem is when you draw the S ones in circles, we get this sense that, oh, they must be in orbitals, they must be orbiting like the planets, because that's what we call them, orbitals. But then you draw the dumbbell-shaped one, and what do you think about in your mind? Oh, it must go in a figure-8 shape. But the nucleus is at the center, how does it get through the, right? You see why these are issues? Right, these are issues, and I'm okay with that. I'm okay with us saying, like, I'm going to use a representation here that I know has some issues that isn't perfect, but it shows enough of something that I think is important. Okay? So, what we're going to say is we're not going to focus specifically on electrons and protons. We're not going to focus on electrons and protons. We're going to say, I think there are positively charged particles and then there are negatively charged particles. And our rule is that the negatively charged particles are somehow free to move, but the positively charged particles are locked into place because they are the fabric of the matter itself. How does that sound? Is that cool? Is that good enough for government work? By the way, so I have an undergraduate degree from college in biochemistry. So in high school, and again, this is many years ago, I had a chemistry class my junior year, I had an AP chemistry class my senior year. I think I got a 4 on the AP chemistry test. I don't know how. This was like we call it divine intervention, right? But I got to college and I had chemistry classes in college, and it was pretty clear to me as I got better at chemistry that I realized I didn't know any chemistry. I know, it seems like this is like a harsh realization, like something very simple. Something very simple. Like, what is carbon? What is carbon?
I don't know.
So carbon, right? What are the numbers for carbon? Does anyone know what the numbers for carbon is? What are they?
I think it's 6.
How do they write it? Like C, is there like a 6 here?
Yeah.
Yeah.
And like a 12 here?
Yeah.
Yeah.
Is it?
Wait,
Yeah.
carbon is 12.0.
Right, we're gonna talk about that in a second, right?
Oh, right.
So does this look vaguely familiar?
Yeah.
Okay, here's a thing that I never understood this. Like, this is like the most bizarre thing. Did you know that it's the number of protons only that determine what an element is?
Yeah.
Did you know that?
Yeah.
How do you all know that? And I was like 23. I like had a degree in chemistry, and I was like, wait, what?
Because that's what Ms. Lee told me.
Well, let's say Mrs. Lee, she's great. So, what does this mean? If you are a carbon atom, you have exactly 6 protons, right? That's the deal. If you have 7 protons,
Something else, I don't know.
yeah, you are something. Would you say you are nitrogen?
Yes.
Right? I think it's actually an 8.
Yeah.
And actually, okay, but this is the problem, is that oftentimes in these chemistry classes, when all they do is talk to you all day, they talk about ions and isotopes
Ugh.
at the same time. That's a little confusing, right? Because carbon, they're like, no, carbon can also be 14. But what they don't tell you is that it's still 6. It's still 6. But what is this bottom number then?
The amount of proteins and neutrons.
So this is the protons and the neutrons together. So normal carbon has 6 protons and 6 neutrons. Fancy carbon has 6 protons but 8 neutrons. But still carbon,
Yes.
right? Still carbon. And then they're like, oh, but you know, to confuse you more, we're just going to add up the total number of all of these and then average them together and like be like that. Like, that's not helping. How could you have, because this says, oh, I have 6 protons, but I have 6.01 neutrons. How could you have a 0.01 neutron? You see why I'm confused? You see what? Yes, right? This, okay. That was,
Taking chemistry.
he's like, I am very confused. Okay, we don't need to talk about that. So, I'm not talking about protons and neutrons. I'm talking about, in your head, some positively charged particles and some negatively charged particles. Is that okay? Is that cool? What happens? If you bring this here, what happens? Did you check your neighbor?
Yes.
Does your neighbor have a sense of what's going to happen here?
Yes.
Yes or no?
Yes.
Josh, what do you think?
I think the negatively charged particle will strike the positively charged particles in bond.
So, this is going to come close to here, right? This negative is going to be attracted to these positives, true? My issue, though, is, Josh, it's going to be repelled by the negatives that are here. You with me on that?
Yeah.
So I don't understand how it's overall attracted when it's gonna be attracted by some but repelled by some others. Patrick Henry?
Well, since it's like overall neutral, like nothing happened because the negatives and positives balance.
Yeah, that's what I thought too, until yesterday, I rubbed the balloon with the fur and I stuck it on the wall, and what happened to it? It stayed stuck. So somehow, it does get attracted. Are you with me on this? Put your hand up. You with me on this? So what we're dealing with right now is this thing called cognitive conflict, right? We have some cognitive conflict. We know it's neutral, it shouldn't be attracted by a neutral, but it was, yes? How? Something has to happen. Go ahead.
Don't the negatively charged particles in the board like move behind and then the positives attract because the positives of the board attract the negatives of the balloon because the balloon's negatively charged, and then the negative charged atoms or negatively charged particles in the board move back. So like all the positives move forward and the negatives move back to the part that balloon's sticking.
Okay,
Yeah, makes sense.
does that make sense? So I think part of this makes sense. Are the minuses free to move?
Yeah.
Go ahead.
Well, like you said, like since like the negative like doesn't attract them, it repels them, so they go in the back, and the positive go in front. Does that make
So-
sense?
I don't know if the positives necessarily move forward, but the
Like the
negatives
negatives
move
move
back.
back.
So the positives can't move.
Okay.
The positive can't move, but the minuses can. So you're saying as I bring this closer, these minuses here get repelled by this minus and they actually move. But what does that do to the front side of the board then?
Makes it positively.
It leaves it overall positively charged, and you're saying that this positive here will pull this negative balloon in and hold it there. That's what you're telling me? Does that seem reasonable?
Yes.
It seems super reasonable to me, all right? And what we do is we have a sense of this, okay? We have a sense of this. Now, what would happen, however, what would happen if this weren't the case? Okay, what would happen if the balloon were actually negatively charged? Okay, what would happen if the balloon were actually positively charged? What if the Josh hypothesis is wrong, and by rubbing the balloon with the fur, we're actually transferring electrons from the balloon onto the fur? What if that were the case, all right? So check with your neighbor. I want to know, would this still stick on here, and what's the mechanism therein?
It
Okay, you
pulls
got
the
me?
negative ones
All right,
towards
check with
the
your neighbor
front
now.
front of it.
You may not sleep, okay? You may not sleep. So keep your eyes open, and if you cannot, I will send you somewhere where it's easy.
Stop.
Okay? You may not sleep.
It's big, it's gonna stay on top.
Lorena, are you okay back there?
Yeah.
What's going on?
I've had it.
What's that?
I've had it. Okay.
You sure?
Yeah.
Okay. Let me know if you need anything, okay? All right, where are we on this? Maggie, what do you think's gonna happen here? Do you think this will still stick?
I don't think it will because, like, since the protons can't move, or the positively charged particles can't move, like, there's no, I don't know, like, I've had a very good chemistry class, but, like, the negative, like, I don't think there's room for the negatively charged particles to move forward, so then,
Oh, so you think that they're blocked by moving? That's
Yeah.
interesting. Let's go, Haggerty, and then we'll go, okay, go.
Well, if the protons can't move, then how would they get onto the balloon?
I think the other hypothesis, he said, so this is the fur here. I think the fur here is, what if you, when you rub the balloon,
Put the fur on.
when you rub the balloon, what if minuses transfer onto here through the rubbing?
Oh, okay.
If minuses transfer onto here, this is gonna leave this overall negative, and this is gonna leave this one overall positive. Is that cool?
Yeah.
When this one over here is different, this one over here is different, here when we did the rubbing, the original Josh hypothesis is that minuses moved on to here. And it left it overall negative and overall positive. Is that cool? So, Megan makes a good point. She's like, I don't know if these minuses can move into this space, okay? What if they can? What were you gonna say?
Oh, cause like they're gonna move over, plus aren't like, since electrons are negative, it'd be like, aren't they like smaller than positives, or we do not know that yet?
They're super small. And in
They're
fact,
smaller
in
than-
matter as a general
You
concept,
don't even count.
most of matter is empty space. Like, we work at a macroscopic level, so like here, like, but most of the matter is really just empty space. There's nothing, and nothing between these things, yeah.
Since they'd be smaller, they'd move, they could like move like around them, cause they don't even count like electrons as mass, cause they're so tiny.
So what you're saying is that if I bring this close to here, these pluses can't move, true? These pluses can't move? So what ends up happening then? You're saying that some of the minuses from the second row are pulled toward the front row? Like here and here? So those minuses move forward? Is that what you're saying? So what then happens to the front side of the board then? It becomes overall negatively charged. Is that a possibility?